Hi folks, Mr. Ackerman here. Thanks for watching. The topic of today's video is frames of reference and relative velocity. Today we're going to talk about what exactly we mean in physics by a frame of reference, or sometimes I write that as FOR. And we're also going to talk about a concept called relative velocity, and we're going to look at how to calculate relative velocities. We're going to do problems in 1 and 2 dimensions, 1D and 2D. So taking a look at the homework schedule, this is section 1.5 in the textbook. The pre-class homework would be obviously to watch this video, and if you get a chance, read through section 1.5 and look at some of these sample problems. In class, we're going to try these two problems here, and then there's some homework questions for later on for extra practice. But today I'm going to do something which I don't normally do, and that is I'm going to leave part of my teaching duties to someone else. There are two videos that you are asked to watch on YouTube. They are not mine, and you'll quickly see that when you watch them. They were made, I think, in the 1960s by a couple of professors from U of T. They're kind of grainy, they're not easy to see, but they are absolute classics. Every physics student in the universe has seen these, and they do such a good job of explaining what this thing called relative motion and frames of reference is that I'm not even going to try to compete with them. I'm going to ask you in a moment to pause this video and jump over to these two YouTube links. I saw these when I was a student, and I'm sure a lot of students still watch them. They're that good. Here's the YouTube link itself. The first one, Frames of Reference Part 1, is about 8 minutes long, and as you can see, you're going to go about halfway through the first half of Frames of Reference Part 2. So that's going to take you into this one here, right about halfway, maybe 3 or 4 minutes in, until they start talking about acceleration. Okay? So when you get to these, here's what you're going to see. You're going to see them discuss what motion looks like from different points of view. And to get an idea of what they're talking about, try to imagine this. Imagine you go home at the end of the day and you get on the bus. Let's suppose that the bus is moving this way. Right now I'm just going to call that the bus. And suppose you get on the bus and you want to walk to your seat. So let's just call that the you. And suppose you leave your friend standing on the sidewalk. Your friend just walked you to the bus stop to say goodbye, and she stayed on the sidewalk here. So here's the question. If the bus is going to the right, and you are walking backward toward your seat to the left, suppose you can walk at an average walking speed, I don't know, maybe like 1.5 meters per second, right? And suppose that the bus gets moving at, I don't know, let's say 15 meters per second. Can you guess what velocity your friend will observe you moving at as a result of the combination of facts that you're on a bus that's moving one way at a certain speed and you yourself on that bus are walking at a certain speed in a certain direction? Anyway, right now pause this, go watch those two YouTube videos, and when you finish watching that, come back and I'm going to pick up right where we left off. Okay? Go for it. Okay, we're back. Now, you've just watched the video, and in the video they did an experiment that was kind of similar to this. Instead of a bus, I believe they were on a cart that could be pushed across the floor in a laboratory. And the two professors were sitting at a table, and instead of a person moving, they had a puck filled with dry ice, which allowed it to glide pretty much frictionlessly. They were pushing it back and forth across the table. So the puck was like the person here, and the cart was like the bus, and you, watching from the camera's point of view, were like this person here. Now, they used symbols like v and u as their relative velocities. Now, our textbook doesn't use those symbols. We use slightly different notation, so allow me to show you how your book would have done this, and I'm going to relate it to a bus, for example. And then you can maybe go back to the video and say, I wonder how they would have related it to the cart and the dry ice puck and the observer. So I'll use a different color so you can see a little bit better. In this case, the bus moves at a certain speed or certain velocity, and that's measured based on how fast it moves across the ground. So we actually call this the velocity of the bus relative to the ground, where b equals bus, g equals ground. So that's VBG, 15 meters per second to the right. Okay? Now you walking on the bus, you're walking at this speed, but that's relative to the thing you're standing on, which is the bus. So this would be the velocity of, let's say, P, the person, relative to bus. So let's call P the person, that being you on the bus. Okay? And the question is, what velocity does your friend observe for you relative to Earth? Because your friend is standing on Earth, so she's going to make a measurement of your velocity relative to her. She's in the Earth's frame of reference, so she measures VPE. And the question is, what will that be? Well, I think most of you intuitively know that if you're going 1.5 meters per second to the left, and the thing you're on, the bus, is going 15 meters per second to the right, your friend's going to measure kind of this minus that. I think you can guess that your friend is going to measure 13.5 meters per second to the right. So how do we show that that's true? It seems that this motion combined with that motion gives this motion. So we write it out as a vector equation. The velocity of the person relative to the bus plus the velocity of the bus relative to the ground gives some combined velocity that the person on Earth measures, VPE. Actually, now I just realized I've made a little mistake here. Instead of E for Earth, I'm going to use G for ground. That's my mistake. I often use those two interchangeably. So let me just erase that E. You've probably been wondering for the last few minutes what exactly I was doing. Sometimes we use Earth, sometimes we use G for ground. I just noticed that. I apologize. Okay, hope you're all okay with that. And now this is how your textbook would write this formula. If you look in your textbook in section 1.5, they use this notation, unlike what the video used, and you just have to get used to it. A really neat trick that they use is the following. If you designate your objects or frames of reference correctly, bus, ground, and person, and if you write these subscripts correctly, they tell you in the book that the middle letters will always be the same, and the outer letters will match these outer letters. And that's kind of the way that you know that your vector equation is correct. Okay? So in this case, would this work? VPB is 1.5 meters per second left, added to VBG, 15 meters per second to the right. Is 1.5 left plus 15 right equal to 13.5 to the right? It certainly is. So this equation does work out correctly, both intuitively and mathematically. And this is how your book does all these questions, once again, so you can use this notation. Now, an interesting thing that arises, or an interesting idea, is the following. Imagine if the person on the bus was a baseball pitcher who could throw a ball really, really fast. Like, say the person could throw a ball at 100 kilometers per hour. And suppose the bus could drive forward at 100 kilometers per hour. Would 100 kilometers per hour forward and 100 kilometer per hour backward cancel out? Would the ball hang motionless in the air? So once again, imagine this situation, if you would. Is it possible that we could actually see an object seem to hang motionless as viewed from Earth when it's clearly moving very fast in another frame of reference? So now what I'd like you to do is go and take a look at a third video. This is the one down here called Vector Addition. I don't know the exact name of it because the video is actually done in Japanese, and I don't speak Japanese, but it's kind of, to me, it's kind of like a Mythbusters sort of thing, and they do such a good job that we're going to watch this together. So let's just hop over to YouTube for a second. Here's the video. You can watch from the beginning, but I'm going to watch from about 3.5 minutes. Here's what happens. They're counting down the time where a van with a pitching machine is going to fire a ball backward. Now, the van is moving forward at 100 kilometers per hour, and the ball is shot backward at 100 kilometers per hour, according to the pitching machine. So now let's watch what happens. It really does look like the ball falls straight down. Of course, once it hits the ground, it starts rolling because of the spin that's on the ball. Here it is in slow motion. Sure enough, the ball falls straight down, which is kind of cool because this means that relative velocity equations that we've been using are correct. So that's just a fun thing to get you started on one-dimensional motion. So this is all one-dimensional. What I'd like to do now is ask you to try a few of the one-dimensional kind of questions in the book, and then once you're done that, we're going to move on to two-dimensional problems. All right, so here we go. In 2 dimensions, what is an example of a two-dimensional question? Well, it's kind of hard to visualize because once you get into 2 dimensions, the motion becomes a little bit trickier. However, a sample problem would be like number 3 in the textbook. The textbook we're using is Physics 12 by Nelson. It says here that a helicopter is flying where the wind is blowing, and the pilot of the helicopter needs to move in a certain direction compared to the ground. Now, if you don't know anything about aviation, you might be having a hard time judging what's going on here. So once again, let's pause and get out of this. Go to a 4th video that I put a link to called Extreme Crosswind Landing. And I just want you to watch this to see what it looks like when you're dealing with relative velocity in 2 dimensions. Now I'm going to play this from about the 20-second mark onward. This is an airplane trying to land at an extremely windy conditions. Now as the airplane goes straight along the runway, you can see it's flying straight along the runway. Look at the direction the airplane is pointed. Okay? I'm just going to go back there. It's actually kind of shocking, but the airplane is pointed well off to the right. Yet he's flying, the pilot is flying straight down the runway. Now you know that means that his velocity relative somewhere off to the right while he's in the air. Well, this is an example of what we call velocity relative to ground and velocity relative to air. And in navigation, in airplane, in flying, for example, there are some special terms for this. So, for example, when they say here that a pilot is flying where the average wind velocity is this over here, the average wind velocity, they're talking actually about the wind itself. So, sorry, I think I drew a line right through the word wind velocity. So this is what we call velocity of the wind relative to Earth. So W is wind and E is Earth. Okay? It says he needs to achieve a velocity of this relative to the ground. So this is going to be the velocity of the helicopter relative to Earth or ground, whichever you prefer. So H is helicopter. And then they ask, so what is the necessary velocity relative to the air? Basically what they're saying, if you go back to this YouTube video, is the following. If the wind is blowing a certain way, and you know you have to travel a certain way relative to the ground, what direction do you need to point your airplane in order to compensate for that wind? Because you see what's going on here is the wind is coming in across the runway, and the pilot is having to compensate for that wind by pointing the plane far off to the right, even as it goes straight down the runway relative to the ground. So let's take a look. If we use the rule that we learned back here for adding vectors and making the letters connect, then let's see how that works out here. Can we make it work? We've got the velocity of the wind relative to Earth. And we've got to say to ourselves, we've got to think that when wind is blowing, then airplanes in the air have to adapt the direction that they're pointed. And so what we end up with is the velocity of the wind relative to the Earth combined with the velocity of the helicopter relative to the wind. That tells us what must be the velocity of the helicopter relative to Earth. So if you think of it like this, the middle letters cancel out and the outer letters give us what we have here. What is this saying to you? It's saying helicopter relative to wind. That's the direction that the helicopter has to aim in the air. Wind relative to the Earth, that is the direction that the wind is blowing. When you combine these two effects in 2 dimensions, you end up with what the helicopter does actually relative to the Earth. So going back to the video with the airplane landing, what the pilot is doing in terms of aiming through the air combined with what the wind is doing tells you what's going to happen relative to the ground. And the formula that we get is this. All right? Now, this is in 2 dimensions. How do we deal with it? I know how to deal with it in 1 dimension. I did that here. How does it work in 2 dimensions? Well, if you think to yourself, well, how do we deal with vectors in 2 dimensions? Well, we do vector components. Then you've got the right idea. What you're going to do here is write VHW in component form. And then you're going to add that to VWE written in component form. And that's going to be equal to VHE written in component form. Now, let's try to draw these vectors really quickly and see what exactly their components are. So, for example, let's just get that going there, north, south, east, west. The VWE is 38 kilometers per hour, 25 degrees north of east. So where is 25 degrees north of east? That would be something like this, with a 25 in here. That's the velocity of the wind relative to Earth. It has a magnitude of 38 kilometers per hour. Okay, so if we do components for the velocity of the wind relative to the Earth, we're going to have 38, and that'll be a cos 25, and this of course will be 38 sine 25. Now they tell you that the pilot wishes to achieve a velocity relative to the ground of 91 kilometers per hour, 17 degrees west of north. Now where is west of north? That would be somewhere over here. A longer vector at 91 kilometers per hour, and also 17 degrees. So right in there. So this is the velocity of the helicopter relative to Earth. So what's that going to be? The x component will be negative. This was 91, by the way. 91 kilometers per hour. So you're going to get negative 91, and that'll be a sine this time of 17 degrees. And this one will be positive 91 cos 17 degrees. Okay, hope you can see that. And now the question is, if you want your plane to actually go this way relative to the Earth, to the ground, and if you know that the wind is blowing this way, what direction do you have to aim? So figure out the x and y components of the velocity of the helicopter relative to the wind, or in this case, the air as they call it. How does this work? Run these numbers through your calculator, get a decimal. This plus that equals that. This plus that equals that. Solve for x and y. Once you have x and y, you can do the usual. You can find the magnitude using Pythagorean theorem, and you can find the direction using trigonometry. And if you check that, you should find that the answer that they get to in the sample problem is the same as what you're going to get to. They're going to do it using triangle math, in other words, sine and cosine law. But we don't do it that way. We use components because, as we've seen, they're a little bit cleaner and easier to use, especially when you're dealing with a lot of vectors. Okay? Just a couple more things before we sign off here. There's some special terminology in this section. For example, you might hear the term airspeed and wind speed, and those will sound confusing because air and wind kind of sound the same. Then you'll hear ground speed. What do these all mean? Well, every now and then at the side in the margin of your textbook, there'll be these little captions that say, "Did you know?" and they'll give you some important information. So this is one of them where I'd like you to do a little bit more research on your own, because you are going to hear some of these terms in class or in the homework, and it would be good for you to know what they mean exactly. And finally, just a few quick applications as far as the water goes. You may have guessed that just like a pilot has to account for the wind when she is steering the airplane, so does the captain of a ship have to account for the motion of a body of water, like a river or the ocean, when steering a boat. Even for a swimmer. Like imagine if you were a triathlete, and let's say you're trying to cross a river during the swimming portion of a triathlon, okay? So the river is flowing along. Let's say the current is flowing this way. Now, what is a current? It's the velocity of water flowing past the ground. W is water. Water flows across the ground. That's what we call a water current. And we know when we get close to a very fast-moving river to be careful because while we stand on the ground, there's no problem, but if we get into the water, it could sweep us away. You're a swimmer, and you're trying to get from point A to point B. Let's say you're trying to get from point A over here to point B over here. Now I'll ask you, if you know the current was flowing to the right, where would you aim? I think all of you know that you'd have to aim sort of upstream a little bit in the hopes that the current would sort of push you back on track, and maybe if you were lucky, you would end up going straight across the river as you had intended. Well, if that sort of thinking makes sense to you, then that's great, because you'll quickly be able to identify what are referred to as the velocity, what are referred to as the velocity of the swimmer, let's say, relative to the ground. S equals swimmer. And the velocity of the swimmer relative to the water. So see if you can make sense of this. Velocity of the swimmer to the water is kind of like the direction you aim, much like an airplane would aim a certain way, because based on the wind for the airplane or based on the water current for the river, that's going to determine where you end up. So when you're doing a question in the book which is going to come up involving a swimmer, see if you can get this equation to work, that the velocity of the swimmer relative to the ground is equal to the velocity of the swimmer relative to the water combined with what the water is doing relative to the ground. And if you get this right, you're going to see, hey, look what happens. The middle letters match up again. The outer letters here are the same as those. We use vector components in 2 dimensions to solve this problem, just like we did here. We plug in the 2 known vectors, and we solve for the components of the unknown, and then we find the magnitude and direction. All right, folks, that's it. The rest of this, when you try the questions in class, we will get a lot more practice. I hope that helps, and I will see you next time. Thanks for watching.